So what we're going to do is we're going to pick up where we left off. When we stopped for the break, we had just set the orientation of our extrusion. So now what we're going to do is set up a couple of other attributes for the extrusion. Oh. All right, so we've already selected. Now you'll notice in your book, these edges are flipped outwards instead of the two that I had. This can vary. So what you need to know is when you're doing extrusion, make sure that all the marching vectors are pointing in the direction that you need them. Once you've done that, then the next thing I do is go to the step size frame and attributes and set your wall spacing. For this case, it's going to be 1e to the negative 4. So up here, if I click on step size, right here, my initial delta S, I'm going to change this to 0.0001 and hit enter. Now, there's a little tip I'm going to give you here. When you're doing extrusion, most of the time you guys already know what your wall spacing needs to be based on whatever y plus value you're running. If you don't, and that's rare, I try to always keep my extrusion wall spacing smaller than this value right here, the minimum surface spacing. The reason being is if it's larger, then when you extrude off your surface, you could be making a cell that is taller than it is wide. Does that make sense? And that tends to lead to increased crossing in corners and problem areas. So I try to keep my initial delta S smaller than the minimum surface spacing as a rule of thumb. Now, we've set our initial delta S, we've set our orientation. Now what we want to do is we want to march our extrusion into the interior of each of these outlets to create this type of OH grid. So I'm going to do that for 25 steps. So this is giving me 25 layers effectively in my boundary layer for these pipes. So I'm going to click on Run and type in 25 and then click Run. Whoa, what happened there? That's not nice. All right, so let's go back and look. All right, all this looks okay. My orientation is fine. Nothing should be changed there. Let me see. Set plane is fine. Oh. All three. What? All right. Just 1 second. Okay, that's what I thought. So what happened there is a mistake on my part. So when I was in the Attributes tab and I set that initial delta S, what I did wrong was I only had some of my outlets selected. I didn't have all 4 of my extrusion edges selected. So I only set my initial delta S on some of the edges, not all. The ones that failed were the ones that weren't selected, and they had the old initial delta S, which is a large value for this outlet. So now, if I select all of them, you'll notice that in the initial delta S field it's blank. And point-wise, whenever you select multiple things and you have a field blank like this, that typically indicates there's a mixture of settings for it. So that's a clue to me of where I went wrong. So let me go ahead and fix this and type in 0.0001 and hit enter. And then go to Run and run my 25 steps in. I'm going to click on OK. So you should see what we have as a result in each outlet is an extrusion that looks like this. Okay? So now to finish off these outlet domains, there's a couple of things we have left to do. The first thing is, for each outlet, we need to pick these 4 connectors and assemble a structured domain. So that'll give us an OH topology. The next thing we're going to do after that is we're going to run the elliptic solver on these domains to smooth them out and optimize the shape, much like what Eric showed you earlier using the floating BC. So here you can see we're going to select these 4 connectors. We're going to select the structured grid type and then assemble domains. So I'm going to zoom out a little bit. And I'm going to use a shift select box to go through and select these sets of connectors. I'm going to make sure I set my grid type to structured, and then I'm going to pick assemble domains. All right, so now I have my 5 structured domains at each exit. I'm going to run them through the elliptic solver just like we talked about. So I'm going to use the selection box again to grab just the outlet domains and go to Grid, Solve. And this is very easy to do. All I have to do in Edge Attributes is change the boundary condition from fixed to floating. And then under the Solve tab, I'm just going to run these for 50 iterations. So now, my OH grids have all been modified. The boundary shape's been modified, just like what Eric showed you earlier, for more optimized shape. What I like about using the floating BC for these types of topologies is, before I did this, the skewness in these 4 corners was really bad. And this significantly improves the skewness in these corners. All right, and this is just sort of going over what we just did in the solver. Here's what those domains look like. The skewness before we ran them through the solver. The maximum value for equiangle skew was 0.9. And then after we ran them in the solver for 50 iterations, it went down to 0.34. So it was a significant improvement in the skewness. So we've got all the domains. So now what we need to do is create our block. This is the easiest step. So we're just going to go in here. I'm going to zoom out a little bit. I'm going to turn off the display of the database too. Let's see. I'm going to select all these domains. I'm going to set my grid type to unstructured. And then I'm going to go to the block assemble command up in the toolbar and click on that. Let's see, it says 0 blocks created, 63 domains unused. So why don't we have a block? Let's look. We have all of our outlet domains created. We have our inlet domain created. All right, so does anybody have any ideas what a typical reason for a block not being created is?
The dimension connectors between the structured and unstructured mesh.
It could be that we missed one of those and it's not watertight. Watertightness is the most common reason for a block failing to assemble. All right, so let's go.
Yes.
Yeah.
To show another point.
Yes, because remember earlier, we undid this step when we were playing around with that, and I never redid it. So he hit the nail on the head. Very observant. So this is easy to fix. You guys remember what the fix was? We're just going to change the view. We're going to grab the connectors, not the domains. And I'm going to change those to 15. They're now identical. So now, if I select all the domains, I should be able to assemble the block. Yep. So, good catch. It's just about always a water tightness issue if you can't assemble the block. All right. So now let's go in and set up some of those T-Rex attributes we talked about earlier. So we're going to select the block and go to Grid T-Rex. For the max layers, I know that in that OH portion of the grid, I set the O grids to be about 25 layers. So I think 40 is ambitious. But I'm going to put a larger value in there that I think I'm going to get, just to let everything grow out to isotropy. I'm going to set 5 for full layers. For this case, I'd like to ensure I get a certain number of prisms and hexes in the initial boundary layer. So I'm going to shoot for 5 layers. I'm going to turn on push attributes. So push attributes is what tells pointwise. If you have an unstructured domain set to a match boundary condition, you can change the characteristics of that domain to match the T-Rex boundary layer. So it can modify the domain itself. And where this is going to come into play is the inlet domain for the entire intake. You'll see it get updated. In the advanced frame, we're going to change the collision buffer. In this case, I'm going to set it high. I have pipes, and they're all growing in. I know they're going to collide, and I want a reasonable area inside the pipes for tets to grow. So I'm going to set it to a large value and use 4. In the skew criteria frame, I'm going to set this to 170, and then we're going to initialize. So I'm going to select my block, go to Grid T-Rex. I'm going to set my max layers to 40, and I'm going to set my full layers to 5. I'm going to turn on push attributes so it can modify my unstructured match domains. In the advanced frame, I'm going to uncheck use default for the collision buffer and increase it to 4. Then I'm going to come down here to skew criteria, and I'm going to set my max angle to 170. This value works well for most solvers. If you're using open foam, you're always going to want to use 160. So, just a note. Now, boundary conditions are the next thing that we need to do, and this is an important stage. So what we want to do here is we want to create all the boundary conditions we're going to need for this mesh. I need one identifying the inlet domains as match. I need one for the outlet structure domains that we created. They're also going to be match. And then I need one for the intake walls. Those are going to be all the other domains that we're going to grow off of. Now, my strategy when creating boundary conditions for T-Rex is to do the easy ones first. The reason for that is if I do the ones that are really easy to pick first, like the inlet and the outlets, all that's left are the domains that go into 1BC. So I can use a trick to select those and assign them so I don't have to pick them out by hand. So let's go ahead and create these BCs. So I'm going to go to New and name this Inlet and set the type to match. Now, you are going to see something here I have not talked about, which is adjacent grid. This type for T-Rex is for a very limited case, and it's where you have a T-Rex block, and it sits on top of an existing structured block or a prism block. And in that situation, you most likely want the layers that grow in the bottom of the T-Rex block to grow so that there's not a volume ratio jump between the two blocks. Does that make sense? So what you would do is you would select that interface domain between the two blocks, and you would set it to adjacent grid, which tells us to get the last cell height from the block underneath it and use that as the initial wall spacing. So I don't see it used a ton, but it is there if you need it. So I'm going to select match for inlet. Now I'm going to create another one, new, call it outlet. It's also going to be set to match. And then my last one, I'm going to click new for, and call it intake walls. That is going to be a wall type, and as soon as I click on wall, delta S is populated with the default of 0.1, which is incredibly large for this case. We're going to modify this to match what we used for our extrusion, which was 1e to the negative 4. All right. So now we just need to go around and assign these boundary conditions. So the first one is the inlet domain. I'm going to select it and then come over here and click on Set for the inlet BC, and you see that the number field is populated with a 1. Then I'm going to rotate this around, and I'm going to use a selection box to grab all those structured outlet domains I just created. I'm going to come over to the table and click on Set for Outlet. Now, my trick is, like I said always pick the easy ones first. Everything that's left that hasn't been set is sitting up here in the unspecified BC. So my trick is simple. I'm going to click on Unspecified. I'm going to use this button called Add to Selection at the bottom of the panel, which selects everything. And then I'm going to click on Intake Walls. It seems trivial, but I routinely work with these really large grids that have thousands and thousands of domains. This trick has worked out for me very well with all those cases. There's always a couple of simple BCs you have to set, and then 500 domains that have to go into one. So this is a great productivity enhancer. All right, so we've set everything. So now there's one more step. You'll notice that when I'm setting up the T-Rex attributes, I completely skipped growth rate. That's because of this table that we've added. So this table at the top of the T-Rex panel essentially is giving you feedback about any structured domains that are set to a match boundary condition. Because when you grow T-Rex alongside structured domains, you don't want T-Rex to modify those domains. In general, we believe structured grids are sacred. Don't touch them, don't modify them. Somebody spent a lot of time making them look exactly how they look. So we want users to be able to make sure that T-Rex is matching them as closely as possible. So as soon as we set those structured domains to a match boundary condition, this table got updated with all the information we know about those domains. So if I switch back over to that T-Rex tab, I can now look at my settings and make sure that they're good for those structured domains. All right, so T-Rex. Yep, sure enough, it's populated. So this is telling me that for all the structured match domains, the initial spacing is 1e to the negative 4. Now, when it started, it was exactly 1e to the negative 4, and you can see that now it's 1.02e to the negative 4. So it did modify that spacing a tiny bit. I don't think it's enough to change what we're going to do, though. The growth rate has stayed at 1.1, which was what we used for the extrusion. So I'm going to use that growth rate with my T-Rex grid here so that it matches. I've already set the wall spacing for my T-Rex grid to be 1e to the negative 4, so that matches up. So I'm going to uncheck Use Default and set my growth rate to 1.1. Any questions about any of this so far? All right, so now we're ready to run this. Get a good view. So I'm going to click Initialize, and I'm going to also expand this. Now, I'll tell you right now, this T-Rex frame is wide. So when it's running, I usually stretch it out so I can see all the information. And there's quite a bit that's going to happen here. So the white that you see is the front growing. This is the vertices advancing. And you're going to see this updated here with the number of cells, the number of layers. You see a number and a slash and another number. So on the left, that's the full number of layers you're achieving. On the right, that's total layers you're getting. So right now, we're 5 for 5. Down here, this is going to be populated once we have interior points begin to stop locally. It's giving you feedback about those points. So it's marching out. We've already exceeded the 5 full layers that I asked for. So who knows how far it could get now. We should start to see some points stop soon. So you want to start looking for red. When you see the first red point, that's actually a really important thing for me. I usually initialize a grid once, and I watch it like this, and I look for that first red point. And then once it's finished initializing, I go look at the surface mesh right there. And I see, was there something wrong with my surface mesh that was the cause of it stopping there early, or did it just stop because it reached isotropy? If it's isotropy, great. If there was an issue with my surface mesh, then I want to fix that and then reinitialize. Okay, so 20 is still going. It's just that you can't see what's going on inside here. Let me see if we can zoom in and get a little bit better view. No. Well, while we're waiting, any questions about what's going on so far? Yeah.
Would it be also possible to use the nice outlet mesh to extrude it to the...
Yeah, that's...
Again, use only T-Rex in the unstructured part because then you would have a nice...
That's definitely a way to do it. Actually, before I put this together, I meshed this like 3 different ways, and I was trying to decide which way I wanted to do for the presentation. That was one of the ways we did it. If I remember right, what I did was, I made the outlet domain, and then I used one of the connectors on the surface as a path connector, and I marched it through like that. And T-Rex in the other section. Right, so one section was all hexa, and then T-Rex was in that part where, you know, the bulb coming into the pipes.
2 steps, not in 1.
Yeah, 2 steps. Okay, it finished. We got 23 full layers and 33 total layers. So let's see what this looks like. Now, I'm going to select my block and go to Examine and Max Included Angle. I'm going to go to Cuts, and I'm going to turn on Enable Cutting, and then change it to a Z physical cut. Now, I'm going to move this cut to the middle of one of these pipes. Now, the only problem right now is I've got a cut, but you can't see anything. So I'm going to turn off the display of domains so it's easier to see my cut. So View, Show Domains is turned off. I'm going to save the cut too. And now let's click on a Z view and zoom in. So you can see the layers that we got in the pipe region and up here. Now here, this is just an artifact of the cut. If I moved this to the center of the inlet, you'd see the layer or the layers. Let's go down to the outlet. Okay, so you see that slight angle there? That's probably an artifact of the domains being 1e to the negative 4 and the volume being 1e to the negative 1.0 e to the negative 4. A very slight mismatch here. There's a tiny bit of an angle between the two. In general, it matches up pretty well. Now, what you're seeing here though, and I'm sure you're all probably wondering about this, is those don't look like hexa or prisms. That's because T-Rex in version 17.3R4 creates tets, anisotets, and then and pyramids. And then when you export, it combines all those into prisms and hexa. Let's see. In version 18, which we are working on right now, all this happens on the fly. And you can get hexas or prisms as you extrude. And this is sort of a preview. And what it looks like in version 18. I'm not going to show you any more because it really is still under development. But we have some lovely hexa layers. So in the version of pointwise that you currently have, you still have tets. And to get hexes and prisms, you have to exit out of examine, export your file to your CAE, and give it a name. And when you export to your CAE, you're going to want to check on this combined anisotropic tetrahedra. What this is going to do is it's going to tell pointwise it can go ahead and start combining those layers of anisotets and the prisms and hexes. It will also touch the pyramids. For this case, when we export it, right now it's around 9 million cells when it's all tets. When we export it, it combines down to 2.1 million prisms at around 400 hexa for a total grid size of about 3.2 million. So it's a pretty significant reduction. Now, talking about this T-Rex cell combination, there's actually a lot of different solvers that can do this. Right now, for this case, I am using, let me see. I'm using CGNS. CGNS is sort of our generic default that we recommend, but if you use any of these other solvers, you should have access to this cell combination on export. And this list grows day by day as we add solvers. Pretty much if your CAE solver supports all the cell types that exist in a T-Rex combined mesh, prisms, pyramids, tets, and hexes, you'll get those cells. Now, when you grow cells off the unstructured domains, I mentioned before, every stack of 3 tets will be combined into a prism. And off structured domains, we talked about those base 7 cells being combined into 1 hexa. And then after that, it falls right back into that same algorithm we use for unstructured. After combination, if it was an all unstructured surface mesh, you could see up to 67% cell count reduction for your T-Rex mesh. Theoretically, if your surface mesh was all structured, you could see up to 88% cell count reduction. But most people I've talked to and I know like to use a hybrid approach. Most people aren't using all structured, all unstructured. They're doing sort of what we had here with the intake manifold, where a portion of their grid uses structured domains, a portion of it uses unstructured, and they're trying to leverage both techniques. So in general, it's usually a mixture. We're going to move on to best practices. Some of these we've already talked about in the course of that case study and questions. So what I did here, the best practices, is I looked at the most common questions and problems we've had from customers over the past years with T-Rex, and I tried to collect those together. The first one that I see crop up a lot is that there are large area ratios in the surface mesh. These usually occur at a domain boundary like this. Typically, it's because people just weren't paying attention to spacing constraints. I've done it myself where I thought I changed all my spacing constraints at the boundaries the way I wanted them, and I missed one, and I got something like this. So what I tend to do is whenever I'm creating a mesh for actually, not just for T-Rex, any unstructured mesh, I create my surface mesh, and when I'm finished creating my surface mesh, I sort of do a visual inspection. I go around the model, rotating it, looking at it, and wherever I have a node junction like this where I have many connectors coming into one node, I usually select all the spacing constraints of that node, and I set them to the same value. It's very safe to do with an unstructured mesh or a hybrid mesh. And that would resolve this issue if you did this as a step before you got to block creation and initializing your T-Rex mesh. Go around and examine all those node junctions to make sure they have similar spacing values. Because you can see here how this creates a surface tri with a really high max included angle. this is going to translate into a volume cell that also has a high max included angle. Now, the other issue that comes up a great deal, and it seems like almost every geometry we see has at least one geometry, one part of the geometry, one surface that looks like this. It's very long and skinny. And if you put an isotropic unstructured domain on that surface, it's not going to look good. And by not look good, what I mean is most people, this is a wing. And most folks that I know, for a wing like this, would want to say, I want 3 cells across the trailing edge, consistently, all the way across. Well, if it was an unstructured domain, you would get 3 cells at the very end, and then it would start making 1 cell across, and then when it got to the other end, it would make 3 cells, and it would look sort of funny. So most people like structured domains for this reason in this situation. So how you handle this type of surface is put a structured domain on it and create a T-Rex mesh where you would get hexa off of that. Or if you want an all-prism T-Rex mesh, create the structured domain here and then select it and go to create diagonalize. Create diagonalize will allow you to put a diagonal edge through each quad, which should result in prisms when you export. Oh, sorry, I almost didn't talk. This little note here is important. So the other thing, whenever you do this, whether you put a structured domain or a structured diagonalized domain, a lot of times I see people ignore the adjacent domains that approach them. That's probably a bad idea because of what we talked about in the first slide. You don't want to see big area ratio jumps in a hybrid mesh. You don't want your area to be this here and then have a huge isotropic triangle on the surface next to it. So what I usually do is if I have a long skinny edge like this, I'll put one of these 2 types of domains on it, and then I'll use T-Rex on the surface domain with a similar spacing to what I have here to try to make those domains match and make the area ratios around the corner smooth. And that'll head off a lot of problems in the volume mesh when you grow off. Another thing that we see a good bit is somebody will create a T-Rex mesh and they'll take a cut through, just like this one, and they'll see this fanning and the isotropic mesh where it connects. Have any of you ever seen this or had this problem? Nope. Typically, this is a result of the surface mesh having too high of an aspect ratio. T-Rex can handle anisotropic surface cells, but there's a certain point at which it's not optimum anymore. And it struggles to connect up and create high-quality tets at the interface. So what I always advise in that case is take your surface mesh and change the aspect ratio. Get it down. I like to get mine down under 40 if I can. The reason being, that's going to reduce that fanning. You're going to have a more consistent growth of your T-Rex layers. You see the fanning's been reduced here by me doing this. And it's really easy to take care of this problem. One way to do it is, let's say if it was a wing, increase the dimensions of the connectors in that direction to bring your aspect ratio down. Sometimes it's a spacing issue where somebody's got very tight spacings on the domain on either side and the center of the domain has gotten very stretched. A third option I've seen people use, but it doesn't have as big of an impact as these first two, is sometimes you can get a little bit of mileage or a little bit of effect out of using an MRQS distribution instead of a hyperbolic tangent. With an MRQS, you have a little bit less stretching in the center of a connector than you do with a hyperbolic tangent. You won't get the same effect as these two, though. If I've got a surface mesh that's quads, I try to get it below 10 for the aspect ratio for the best possible results in the volume. If I've got an unstructured surface mesh, I try to get the aspect ratio generally under 40 for the best results. And you can also use that aniso-iso blending factor that I talked about earlier. You can use it, bump it up to 1, which is the maximum, and that will also help the transition from the high aspect ratio surface cells. We see this one a great deal. So somebody says, well, my T-Rex cells stopped too soon. They look great here. I love how they look mid-chord, but I don't have any up here at the leading edge. And I don't have any back here at the trailing edge either. What happened? Well, if you zoom in on those two areas, at the leading edge, you can see T-Rex growing, right? Looks good here. The thing that clues you into what's happening here is this last cell that was a T-Rex cell. That cell is perfectly isotropic. Remember, one of the stopping conditions of T-Rex is it stops when the cells hit isotropy. So if your initial delta S is the same as your edge length locally, you're not going to get any T-Rex cells. It stops immediately. And that's the same thing you see here at the leading edge. Right here, the edge length is larger than the initial delta S, and as we get closer and closer to the leading edge, it approaches the initial wall spacing. So we don't get any T-Rex layers. So there's a couple of ways we can try to solve this. We can set the full layers attribute to a non-zero value. This is going to force the T-Rex cells to go past isotropy. So they're going to be anisotropic in the direction normal to the surface. It will still stop locally if we encounter one of these conditions, a negative area, a collision, or skew criteria is violated. But it will push it past isotropy for these scenarios. The other one you could do is you could change the spacing of the grid point so that the edge length locally is larger than the T-Rex wall spacing. That would also give you some cells. And I will tell you, in general, I use a combination of these two solutions. When I run into that, I set full layers to a non-zero value, and then in some areas of the grid, I change the grid spacing too on the surface. If you look at an example of this, in this case, I've just used one of the solutions. I've just set full layers to a value greater than 0. If I remember right, I set it to 3, and you can see that here. I've got 3 nice T-Rex layers on the leading edge. I love the effect, actually. However, the trailing edge for the same setting looks awful because I'm pushing it way past isotropy for this. So ideally, what I would do here is I would leave the leading edge alone, set full layers greater than 0, and back here, if I could, I would increase this spacing in this direction, just a little bit. Okay, gaps are always an issue when making unstructured meshes and getting good quality grid in the gaps. And there's a lot of approaches to solving this problem. I'm going to show you a couple of them. In this case, this is the back end of a submarine. This is a control surface. And in this particular grid, the gap was modeled between the control surface and the submarine surface. So this is the initial surface grid that was created on the submarine, initial grid created on the control surface. And as you can see, right here we're showing the cells that have a max included angle greater than 160. And there are a lot of problem cells between these colliding T-Rex fronts here. So from this picture, can any of you tell me the first problem that exists, the first issue that we should be concerned about? What stands out as being wrong here? So on the submarine, you can look at the size of the cells, the edge length here, growing off the submarine. That is probably equivalent to 2 of these cells. There's a huge mismatch in cell area between the submarine mesh and the control surface mesh. That right there will cause all kinds of skewness issues in a gap. So let's march on. So he hit the nail on the head there. Mismatches in cell area between the approaching fronts causes a lot of skewness. Also lack of space. Very definition of a gap problem. So we're going to get those pancake tets that you saw. We're going to lose resolution in the gap when this happens. And we're also going to have a reduced number of boundary layers, which probably is one of my biggest fears. So there's a bunch of solutions. I don't always use all these. I don't throw my entire bag of tricks at every mesh. I'll pick one or two of these things, I'll try it, I'll initialize it, see if that improved my results, and then do a little bit more if it didn't. So the first thing I usually do is increase the collision buffer. And I'd say 70–80% of the grids that we work with, a collision buffer of 2 works very well for these gap problems. For that intake that we did earlier, I tried 2. I wasn't happy with the quality of cells I was getting. I bumped up to 4 and saw a huge reduction. Another thing I might have done for that intake would have been to bump the max angle down even further. That would have retarded the growth of the T-Rex layers and given even more room for tets. I set skewness criteria. So I say don't generate T-Rex cells that have a max angle higher than this. If you're using open foam, that needs to be 160, period. Other solvers are more tolerant of included max angles, and I've seen some go up to like 178, 179. What they usually wind up doing is if they have a really flat cell like that, they just locally run first order around that cell and then second order everywhere else. Not a great thing. I would prefer to avoid that if I can. So I usually stick somewhere between 160 and 175 depending on the solver. I also typically use centroid skewness, and I use values between 0.6 and 0.7. Open foam, in this case, also likes lower values of centroid skewness if you're an open foam user. Other solvers, you can go a little bit higher. I make the cell areas in approaching fronts closer in size, and there's a few ways to do this. I can select those domains, and in the unstructured solver, I can set the min and max equilateral edge length control to the same value, and then refine them. It's not going to make them match identically, but it's going to make them very similar. The best thing to do, I think, is try to create an identical grid across the gap. If you can do this, this is optimum. Usually this involves selecting one of the domains and projecting it across the gap on the other one. You can use a smaller wall spacing for domains in the gap region. So what I'll do is in T-Rex, I'll have 2 BCs for wall domains. I'll have one that is the body of the aircraft, car, submarine, whatever. And then I'll have a second wall domain BC that is just for gap regions. And I might set it an order of magnitude smaller than the spacing everywhere else. What that typically does is it enables me to get more layers in that region. And between the domains that are the normal wall spacing and the domains in the gap, pointwise will smoothly interpolate between those domains and the initial delta S. It's a little bit of a cheat, but it works very well. And then you can also use isotropic seed layers to get more resolution in the gap. This last one takes the most effort, but it can be really nice if you need hexes in your gap region. Some folks like to create a hex filler block in the gap between whatever the 2 objects are. In our case, it's a control surface and a submarine. You can make a structured block in there and then grow T-Rex off the outside of the filler block. So in this case, I took the domain on the bottom of the control surface and I projected it down into the submarine. I recreated the domain around it, and then I reinitialized it. Oh, I also set the collision buffer max angle. So I didn't use all those solutions. I just used a couple, just so you can see how grid's not all the way there yet. There's still more I can do, but it's a move in the right direction. The grid's already starting to look better. For me, there's still, the resolution could be a little bit better. I could have more points here. I might turn on ISO seed layers. There's more you could do, but my point with all of this is there are several solutions. Not all of them are appropriate for every grid. Play with them, try them out on your specific case, and see what you like best. Now, this is one of the last problems that we've run into. We often have people that have a big multi-block structured grid system, and there's one component to it that is just so hard to create a topology for. It would be a lot of extra work to make it structured multi-block, that section. So they want to just put a T-Rex block in that area instead. And you can do that. You saw a little bit of this with the intake manifold, but what you would do is, in this case, this was for a wind energy case that we got. We made a T-Rex block around the wind turbine. Everything else around it was structured. And we just set all these structured side domains to match. And we used the trick that you saw with the intake manifold where we made sure that the growth rate was similar, the spacing was identical, and it matched up really well. So there's only one trick left here that we didn't talk about, and that is if you can modify the structured grid at all, if you can set the distribution of the connectors off the surface to geometric, that will make the match even better. Most people by default use a hyperbolic tangent distribution for their structure grids. Hyperbolic tangent does not use a geometric growth rate, it varies. So there can be some variation between it and T-Rex in that situation. If you make the structured grid have a geometric growth rate off the surface, you're going to see a better match with T-Rex. And this is what you see in that situation. So it allows you to use the best of both worlds and have a little bit of flexibility. So that's it for our presentation.